Hello, my name is Luis Magadan, and I'm a PhD student of computer science at the University of Oviedo. I'm going to present the paper Cluster Wireless Sensor Networks for Building Energy Management Applications. The use of building energy management applications has increased in recent years, not only because it reduces our electricity bill, but also because it contributes to the fight against climate change and global warming by reducing the amount of energy used. According to a recent study made by the United States National Renewable Energy Laboratory, a 60% of reduction in building energy will be essential for achieving a 100% renewable energy grid. Another study carried out by Deloitte reveals that a reduction in the use of electricity in different domains such as industry, buildings, and also transport will be necessary to achieve net zero ambitions. In fact, around 48% of the energy used comes from buildings. To be more specific, approximately 44% is used in residential buildings, or what is the same, our homes, and the remaining 4% is used in commercial buildings. For this reason, building energy management applications have been used in the recent years. Most of the wireless sensor networks used nowadays use communication protocols such as Zigbee or Z-Wave, which facilitates the creation of a mesh network of nodes. The problem is that these protocols lead to unbalanced energy use, making some nodes to run out of power earlier than others, because they are near the sink and in consequence they receive more packets and they make more communications and process more data. If all the nodes that are near the sink die, the mesh network loses its connectivity with the sink, producing an energy hole. The same could happen in other parts of the network, letting some areas uncovered and uncommunicated. Other common problem in this type of wireless sensor networks is the existence of uncovered areas. Other problem of this kind of protocols is that they don't allow a fog architecture, which helps to reduce the amount of data transferred, processed, and stored in the cloud. This is due to a lack of control and the enormous number of communications in the network. Without a fog architecture, the amount of data to storing is bigger, and in consequence, storing this data in the cloud will be more expensive. For avoiding this problem, Bluetooth Low Energy could be a great alternative as a low-power communication protocol. It is a low-battery version of Bluetooth and is supported by many devices, such as mobile phones, computers, multi-sensor models, Raspberry Pis, etc. It has a bit rate of 1 megabyte per second and a theoretical maximum range of 100 meters. It also offers the possibility of building a mesh network, but this kind of feature is supported by few devices. The battery consumption of this protocol is less than any other thanks to its reduced frequency band and shorter protocol data unit packets. Other protocols used in terms of creating a wireless sensor network could be better approach to mobile ad hoc networking, also known as Batman, which is a proactive protocol which enhances OLSR due to the division of the knowledge of the best routes between the nodes that form the mesh network. This division of the knowledge leads into a reduction of the network overload and also in a reduction of memory usage to store the best possible routes between the nodes that compound the network. In this case, only the neighbor nodes store the best route to their neighbors. In this work, we present a wireless sensor network which follows a cluster approach. The first layer is composed of multi-sensor modules, and the second layer is composed of heterogeneous gateways and cluster headers. The first layer follows a star topology, where the central node is a gateway or cluster header which manages a set of heterogeneous multi-sensors modules using Bluetooth Low Energy. The second layer follows a mesh topology using the Batman protocol. All of the nodes have access to the internet and use Wi-Fi to improve its throughput. The use of redundant nodes helps to achieve their resiliency. The devices used as gateways and cluster headers are Raspberry's Pi4 and Raspberry's Pi3 Model B+. The function of the cluster headers is to transform and forward the data sent by the endpoints through the mesh network until it achieves the gateway where then it's sent to the cloud or IoT platform. Both cluster header and gateways control a set of endpoints and perform the necessary transformations and operations on the data received, facilitating the implementation of 4 approaches there. 4 different multi-sensor models are used as endpoints. As you can see here, the red one is the sensor tag CC2650. The white one is the smartphone DA14580. The blue one, the sensor tile box, and the other one is the blue tile. Their function is to gather data from the environment and send it to the cluster header or gateway following a star topology via Bluetooth Low Energy. Once the topology was designed, the next step was to dimension it. This means defining the maximum length between the different devices that make up the network. To do this, a study is made on how the RSSI between the devices changes as the distance between them increases. As it can be seen in the table, a RSSI level over -30 dBm represents the best signal between devices, and RSSI between -30 and -80 is very good for applications that need reliable package forwarding. In cases that the RSSI level is under -80, it's very difficult to carry out communications without any problem. Due to this, the RSSI threshold established was -80 dBm. First, an analysis of the maximum distance was carried out between cluster headers and gateways. For this experiment, the gateway was positioned at a fixed point, and a cluster header was moved to different distances from the gateway without any obstacles in the middle. The results obtained showed that after 14 meters, the RSSI level starts to be under the threshold. So it was decided to establish 14 meters as the maximum distance between gateway and cluster headers. The same experiment was performed between endpoints and gateways. In this case, the results were different depending the endpoint, the type of endpoint. In the case of the sensor tag and sensor tile.box, the maximum distance was set at 9 meters. However, in the case of the blue tile and smartphone, was set at 8 meters because the RSSI at 9 meters was very close to the threshold. After establishing the maximum distance between the devices, an analysis of the network performance was carried out, studying throughput, latency, and also jitter between gateways and cluster headers, according to the number of hubs between them. For this performance analysis, a scenario was developed. This is the one that we saw here, where the gateway was directly connected to the router via Ethernet, and 3 cluster headers were connected in a chain through the Batman protocol. All cluster headers are 14 meters apart, and all the tests were done 30 times per round, each round separated by a period of 5 minutes, with a total of 6 rounds. In the table below, the minimum throughput obtained is shown. In this case, the maximum throughput with one hub is around 3 megabytes per second, with 2 hubs around 600 kilobytes per second, and with 3 hubs around 100 kilobytes per second. In all the cases, the throughput obtained is enough to carry out the communications without any problem in a building energy management application. In the next table, the maximum latency obtained is shown. As it can be seen, the latency for one hop is around 1.34 milliseconds, with two hops around 3.33 milliseconds, and with three hops around 3.91 milliseconds. The latency obtained in all the cases is enough for carrying out the communications without any problem again. An analysis of the jitter was carried out as well, but the results of this test were not as relevant as the previous one. As it can be seen, the maximum jitter for one hop is 177 milliseconds, for two hops 530 milliseconds, and for three hops 452 milliseconds. In the analysis of both throughput and latency, it can be seen that the higher the number of hops, the worse the results obtained are, being sufficient in all the cases to carry out the communications without any kind of problem. Finally, an analysis of the CPU and memory usage on the gateway while using the Batman protocol was carried out. This graph shows how the CPU and memory increases as the number of cluster headers in the network changes from 0 to 10. As it can be seen, both CPU and memory usage is extremely low, showing an exponential tendency in the case of the CPU usage and a gradual tendency in the case of the memory. The next step was to implement a building energy management system following the dual-layer wireless sensor network previously defined. This prototype was deployed to monitor light level, temperature, humidity, and also barometric pressure in the Computer Science Department building at the University of Oviedo. That is a building composed of four floors. As you can see in this dashboard, we are monitoring temperature, humidity, the light level, the barometric pressure, and also the battery of the devices, of the endpoints. For this prototype, three Raspberry Pi 4 were used, one of them working as a gateway, and the other two as cluster headers. A Raspberry Pi 3 model B+ was used as another cluster header. A total of 16 multi-sensor modules were used. Sensor tags CC2650 and 4 smart bonds DA14580 were used to monitor rooms because they have a light sensor. In the case of sensor tile box and blue tile, those were used to monitor building halls and corridors. The gateway was placed in the ground floor, and the cluster headers were placed in the basement, first and second floor. On this prototype, a similar analysis to the previous one was performed, studying throughput, latency, and jitter between the cluster header of each floor and the gateway that was located in the ground floor. The throughput obtained for all the cluster headers is enough to carry out building energy management communications, being better in the case of the cluster header placed in the first floor. The same occurs with the latency. In that case, the cluster header which offers the best latency is the one placed in the first floor. As it can be seen, all of them offer a latency near 1 millisecond, which is perfect to carry out the communication of a real-time application. Jitter is similar to the throughput and latency analysis. In all the cases, the cluster header that presents the better performance is the one placed in the first floor, while the one that presents the worst results is the one located in the basement. This is mainly due to the fact that the ground floor, first floor, and second floor are connected by an open inner courtyard, while the basement is separated by a concrete floor from the ground floor. The main conclusions of this work was the design of a wireless sensor network that uses Bluetooth Low Energy to carry out the communication between low-cost multi-sensor modules and low-cost gateways and cluster headers, using better approach to mobile ad hoc networking, or also Batman, to create a mesh network between gateways and cluster headers. Due to the use of redundant gateways and cluster headers, we avoid the problem of uncovered areas. We also prevent energy holes and facilitate the integration of a fog architecture by taking advantage of cluster headers that are connected to the power grid. Future work of this work will be focused on using this wireless sensor network in more challenging scenarios, such as industrial Internet of Things or healthcare. That's all. Thank you so much.